Good afternoon, everyone. Thanks for staying to the last session. My name is Dr. Cody Corbin. I am a materials chemist at Sandia National Labs, and I want to start off with saying this work is funded by the Laboratory Directed Research and Development Program, which all DOE National Labs get internal funding for. And this is, compared to all the talks I've seen, I feel like more of a lower TRL, more materials-based talk compared to more devices and things like that. So coming from a chemist, that's probably makes sense. So our goal is to use polydiacetylenes for chem agent surrogate sensing. We can't use chem agents, others can, but surrogates are what we can. I don't know if we want to work with them, but surrogates are good. So why? This is the state of the art used by the U.S. military when it comes to warfighter safety in the field. These are from the 70s, and there has been no update on these types of things at all. So again, our goal is to have a proof of concept with a novel material set to try to update these types of things farther down the TRL scale. So this is called a JCAD. It's a Joint Chemical Analysis Detector. It has, if I remember correctly, ppm to ppb level sensing. This is one per platoon. It has a short battery life, in my opinion, and it is actually can be compromised by humidity. So it's not the greatest thing ever, but it does have sensitivities that are relevant, and it's expensive, not ideal. From an individual level, for a chem bio soldier, there's these paper kits. So this is pure passive sensing, a paper vapor, and there's liquid-based sensing here as well. And so I don't know where this name came from, but what's ironic here is that hazardous reagents are used in the sensing of this. So when I say what they're trying to sense, things like VX, G agents, things like that. Prone to false positives. If you note, this is a quote here that this is not an alarm. This is kind of an analysis after there's been a presence of agents. And so before putting on chemical protective clothing, which is heavy, hot, all of these other things, they want to confirm that there has been exposure. So a lot of my slides have these, which is kind of a quick summary, a blurb present, which I hope helps. So essentially, replacement technologies are needed. We're 50 years down the line here. And so our goal, passive and optical sensing devices are needed. Ideally, if you can get one in both, that would be fantastic. Okay, some other background and recent work. Colorimetric sensing arrays, these problems, for everything here when it comes to all sensing arrays, mixtures of agents, contamination with agent side products. If these agents are synthesized, that's what I'm talking about, side products. The balance of sensitivity versus concentration. Some recent work funded by the Defense Threat Reduction Agency from about 4 years ago. This was some, again, early TRL work, and this is a huge array of materials, if you can see here. This is 54 minutes after exposure, which is way too long if you're actually exposed to an agent. And they did test Windex versus the actual agent VX. And yes, it works, but all of these materials shown here are part of this work. And so logistically complicated, time is not ideal. I'm not saying we can fix that, but there's a lot of improvement that can be made here. And so that's our impetus. It's colorimetric only. So what we would like to do is provide a single material type with a faster response rate, at minimum, would be a win. Okay, so that's where polydiacetylenes come in. From now on, I will probably associate this with PDA. There's a lot of acronyms with P up front. I apologize. I will try to explain each, and so it's clear. So how do these work from a sensing perspective? You will see these in the chemical sensing literature all over the place if you haven't already. And so they're really useful. A diacetylene molecule looks like this. This is a carbon chain here. The diacetylene piece is here. And here is a chemical head group which you can functionalize, do some synthetic chemistry on, which is very important, actually. So these self-assemble on a surface, or if they're dissolved in the right material, they can form micelles. 254 nanometer UV light cross-links them, and this is shown as blue because now you have a visibly blue material. This is colorless. This is blue. If you turn this 90 degrees, all of these are in the same plane. And then upon a stimulus, and this again, so the stimulus can be solvents, heat, in some cases mechanical with the solid material, any form of energy. There's a molecular perturbation down this, and so these kink, if you will, And that, by the way, this is conjugated. That's a key thing here. This conjugation is disrupted because of that molecular perturbation, thus changing the pi bonding, so now your visibly blue has turned to visibly red. And there's a conductivity change because these are semiconductive materials. The reversibility of this is dictated by the head group chemistries, whether if they like to interact with each other, they may be reversible. If they don't, they would be irreversible. And so there's the micelles I mentioned earlier, so diacetylene version PDA. So this is the mechanism of how these work, and I want to stress that this color change is specific to the head group chemistry and the stimulus itself. So if you pull out the red, green, blue response for each of these before and after, they're very specific. So again, jumping to, this is one piece of a lot of literature for chem sensing with solvents. So here an array was made of 8 different PDAs, and when I say different, again, the head group chemistry is different for each one. And you can see just by the controls that each one is slightly different even by the eye. I don't know why this one's red. It's always confused me, but we'll move on from there. So these are all the solvents tested here. And if you just look at the first two, which is kind of, this is what drew me into this, pentane and hexane. You can't get any more chemically similar than that. And yet there's at least 3 here, where it's visibly different and thus quantitatively different if you pull out the RGB. So the array aspect has been proven here. There are 2, as far as I last checked, 2 literature references for doing chemical warfare agent sensing with these materials. This was done with 30 seconds of vapor exposure, and sensitivity level colorimetrically was down to, or you can see the difference by eye at 160 parts per billion after 30 seconds. But the authors state that even within 10 seconds, you can start seeing this. So between this, and here's liquid, that reacts faster, and this is, again, surrogates, not the agents. But between this concept and this, bringing in the array for chem agent sensing, that's where the project proposal concept came from, to where ideally we hope to pull out via the unique RGB responses and the electrical semiconductivity changes responses from these, that we can pull out information on what agent for emergency response and military purposes this could be used for. So the most device thing about this talk is IDEs. Doesn't go much more past that. That's what I was talking about. So we are putting our material on IDEs, and we're doing electrochemical impedance spectroscopy for the electrical characterization. Okay, so again, early materials work started here with integrating commercial PDA, which is, I'll show you the structure in a moment. The next slide will have a synthesis of the ones made in these manuscripts here, but we're using the stock material from like Sigma Aldrich and trying to integrate them into 3 different polymer matrices, Sealguard 184 silicone, PVP, PVA. Each of these is another variable to where you can potentially tune selectivity or sensitivity just because of hydrophobicity or hydrophilicity. At the time, before this talk, we only had 1 surrogate DMMP, but we had some other things, and we're going to do more. Again, later slide. There are some other things that are on hand. DCM always, which is now considered toxic by the world and will try to go away soon. Trichloroethylene and tributyl phosphate, which is a nuclear material extractant for uranium. So there's a security side of this too. So here's the IDEs. We put our material on them, drop casting initially. We haven't spin coated anything. And then we are developing a camera system here with a color card. So there is a reference for the colorimetric piece of this on top of the EIS side. Okay, here's the syntheses. These are what the authors on 2 slides ago made. I'm only showing the final step here. There was some others. It's not that long. The initial starting material is so this is the commercial material, and now this says PCDA. That's the monomer. So there's C in there. It gets confusing. But this, the carboxylate's what's functionalizable. These are the groups that actually can chemically bond to an organophosphate. Not mustard, but organophosphate, and you can get a color change. I do want to stress, you do not have to have a chemical reaction, as noted by the heat aspect of this, to get a color change. Intramolecular forces can do it alone, which is fascinating. Okay, so here are EIS results or Nyquist plots for a lot of these, and this is so we're using neat liquids first to say what sensors are best here, and then we'll do our vapor exposure after that. So here's controls, which should just act as insulators. And so if you see, this is PVAs, this is PVP, this is silicone. All of them act as insulators, no response as expected. What was not expected is that, so these are non-UV exposed systems, so it's the diacetylene monomer inside of the polymer. We're getting, this is a RC response, resistor capacitor response. This is what we want. What we were not expecting, and there's just been no testing on it, is that we are getting responses even better than the UV exposed versions, which aren't as good except for the polyvinyl pyrrolidone one, which has been shown in the literature to be very responsive. So key thing here is, at least from an array or sensor perspective, perhaps we don't need PDAs all the time. Perhaps maybe some can be DAs. We just don't get the colorimetric piece. We only get the electrical aspect because we need the PDA, which is the blue, to get the color. Okay, so there's a lot of content on this slide. So there's two sides of this slide. One is comparing PVP polymer that have both been UV exposed. So this is PVP and PVA. And I just want to note, so I don't have the pictures of this because we didn't have them for this slide, and I apologize, but this did change color, and this did not, and their EIS responses. So blue is before sample, before TVP exposure, red is after, and so they are different, and the fact that one changes color and one doesn't is great. The more uniqueness we get, the better. On this side, the polymer is the same, and one is UV exposed and one is not. Now, neither in this case have a color change, but their EIS responses are also different. And again, this is specific to trichloroethylene. All of the silicone samples, most of them did not respond, which makes sense, probably due to its hydrophobicity, so we're probably not going to use that anymore. And then DCM, actually none of them responded, which may be due to the volatility, because between when the stuff was exposed and the analysis time, there was a time point where it could evaporate. We do need to determine if results are statistically different. Here is a picture, just an example of what this looks like. Uncross-linked, blue material, and red. And so in general, that's what these look like. Okay, I know I'm down to my 3 minutes here. I'll try to hurry. This is other work related to tamper indication. I want to just stress here that there are 10 different PDAs here. There's a tie to the rest of the stuff. And that if you just note, these are all the different stimuli we tested, and this is for international nuclear safeguards. There's lots of solvents, lots of temperatures, lots of concentrations of certain things, and if you do this classification, gives us more confidence. We're going to do this with the chem agent surrogates, that if you have your prediction here, and this is 40 different stimuli, and in the true, almost all of them, 98% we can pull out correctly, which is amazing, compared to, especially since a lot of these are similar solvents. And even if you can't pull out the specific identity, you can say, oh, it's an alcohol, oh, it's an aliphatic, oh, it's an aromatic. You can pull out more information, which is still useful. So if we can say an organophosphate versus a mustard, that would be fantastic once we do this. Okay, there's an acknowledgement slide is after this. So what we plan to do next is to, we need to get limits of detection. We need to integrate the PDAs we synthesize into these polymer matrices. I say these three surrogates. There's actually more. So everything green and yellow here are the surrogates we're going to use. So DMMP, we already start. There's these three mustards, and diethyl chlorophosphate's one of the reference materials that they used as well. When it comes to the silicone-based, this is the only one I showed, I realize now, but these are the silicone-based systems. There is an aging effect. This has not happened in the solid material on like the slide before. That doesn't happen here. There's no aging. So there's a lot of reasons for this. That could cause this. Don't have time to get into it, but we think we know why. Mixtures, we're going into this the next year, which is going to be the most challenging part. And finally, this is the team. I just want to acknowledge them. We have a chem team, sensor team, and stats team. Thank you for your time. If there's any questions, I'd be glad to answer.